Welcome to your asynchronous session for week number 4 for Algebra 2B. We're going to talk about lesson 17, a little bit about probability. So the objective for today's lesson is that students will be able to calculate simple probability, theoretical and experimental probabilities, and complementary events. So we're going to start out with some definitions. So we first need to know what a set is. A set is a collection of distinct objects. An element is each object in a set. Theoretical probability is a probability based on reasoning written as a ratio of the number of favorable outcomes to the number of possible outcomes. Experimental probability is a ratio of the number of times an event occurs to the total number of trials. So those are some of our definitions for today. So let's go ahead and start doing some problems. So we're first going to talk about different types of sets. So the first one we have there is set C is a subset of set B if every element of C is also an element of B. So we have a Venn diagram picture of it there, so you can see that C is completely within our circle for B. So that means that C is completely in B. That means it's a subset because the whole set of C is inside the whole set of B. So the notation that we do is C subset B. So that sideways almost looking C there in between the C and the B is our subset symbol. So let's go to our next one. The intersection of sets A and B is the set of all elements that are in both A and B. So if we look at our Venn diagram there, we have A and B drawn, they intersect. So see the darker shaded portion there in the middle, that is where they intersect because that's where the two circles overlapped each other. So the way that we write an intersection is we have A and then what looks like an upside down U. B, so A intersect B is what that says. That's where the two intersect each other. So our next one we have there is the union. So the union of sets A and B is the set of all elements that are in A or B. So if we look at our Venn diagram there, we just have the whole entire shaded region is of all of A, all of B, including that intersection. So that means anything that's in A and anything that's in B is part of this union. So the way that we write a union is we do A and then what looks like a U, B. Now the last one we have down here is the complement of set A is the set of all elements in the universal set of U that are not in A. So if you look at our diagram, we have our set A, and then the shaded region is everything outside of set A. So that's our complement, everything that's not in set A but that's in our universal set. The universal set is just all possibilities. So maybe we have a universal set of like real numbers is what we're dealing with. So we have then set A may be like only the prime numbers. So our universal set, so the way that we write a complement is we write A and then just like as if we had an exponent, we write a little c there as like a little exponent to it. That represents that it's a complement. So now let's talk about some theoretical probability examples. So what is the theoretical probability of rolling a 3 when you have a dice with sides numbered 1 to 6? So theoretical is, well, what do we expect to happen? In theory, what should happen? So what are our chances in theory of rolling a 3? Well, if we look, we have a normal dice is numbered 1 to 6. So we could either roll a 1, 2, 3, 4, 5, or 6. So that's 6 possibilities. So to figure out our theoretical probability, we're going to take the number of favorable outcomes. So if we're going to roll a 3, that means there's only one choice on our dice, that's a 3. So we only have one favorable outcome. Divide it by the number of possible outcomes. Well, we have 6 total possible outcomes because we could roll 1, 2, 3, 4, 5, or 6. So we're going to have 1 out of 6 is our probability. So when we do that division, we get a decimal. Now when we deal with probabilities, we need our probabilities to be as a percentage. So we need to change that to a percentage. So the way to change that to a percent is either to move the decimal place 2 to the right or multiply by 100. So we get that the theoretical probability of rolling a 3 is 16.67%. So let's do another example. What's the theoretical probability of rolling a 5 or 6 when you have a dice with sides numbered 1 to 6? So again, we have 6 possible outcomes just like we did before, but this time we're rolling a 5 or a 6. So that means we have 2 possible favorable outcomes because there's a 5 and there's a 6 on the dice. So that means that we could potentially get this a lot easier. So we have 2 options that are favorable out of the total of 6 options that we could possibly have when we roll a dice. So when we divide it, we get our decimal. Remember, we need to change it to a percent, so either move the decimal place 2 to the right or multiply by 100. So we get that the theoretical probability of rolling a 5 or a 6 is 33.33%. So go ahead, pause the video, and see if you can do this one of figuring out what the theoretical probability of rolling a 1, 2, or 4 is when you have a 6-sided dice. Alright, so now that you've had a chance to do that, let's go ahead and look at it. So if we're rolling a 1, 2, or 4, that means we have 3 outcomes that are favorable out of the total of 6 possible outcomes. That means we got 3 out of 6. So when we divide, we get 0.5. Change that into a percentage, and you should have received that our probability of rolling a 1, 2, or 3 is 50%. So see if you can now do this theoretical probability. Instead of using a dice, now we have a bag of marbles, which contains 2 red, 1 yellow, 3 green, and 3 blue marbles. What is the probability of drawing a red marble? So remember that your formula is the number of favorable divided by the number of possible outcomes. So go ahead, pause the video, and see if you can figure out the probability of drawing a red marble. Alright, so now that you've had a chance to do this, if we look at our problem, well, we only have 2 red marbles that are in our bag. But we need to know the total number of possibilities, so we need to add up how many total marbles we have. So we have 2 red, we have 1 yellow, 3 green, and 3 blue. So that gives us a total of 9 marbles in our bag. So since we have 2 reds and we're looking for red, we're going to have 2 out of the 9 are red in the bag. So we have a 2 out of 9 chance of pulling out a red marble. So that's 0.222 as a decimal when you put it in a calculator. And then remember, we need to change that to a percentage. So the theoretical probability of drawing a red marble is 22.22%. So that means if you were to have this bag of marbles and you reach your hand in there and pull out a marble, you have a 22.22% chance of it being a red marble. Alright, see if you can do this one of what is the probability of drawing a green marble. Go ahead and pause the video and see if you can figure it out. Now that you've had a chance to pause the video and figure this one out, let's see if you got it right. So there is a total of 3 greens out of the 9 marbles in there, which gives us a probability of 33.33% of drawing a green marble. So you got a little bit better shot at drawing a green marble than you do a red marble. So now let's talk about experimental probability. So experimental probability is different than theoretical, because theoretical is all in theory. Like, oh, if I have this, this is what I expect to happen. Where experimental is, oh, now we did the experiment. Here's what we got for our experiment. So if we flip heads and tails, if we flip a coin, we have a table there that tells us when we flipped a coin 50 times, 26 times it was heads and 24 times it was tail. So this is experimental because we actually did an experiment. We actually got data, collected data from doing an experiment. So we want to know what's the probability of heads. Well, to figure out your experimental probability, you're just going to take the number of times the event occurred divided by the number of trials. So if we're looking at the probability of heads, when we flipped the coin, we got 26 times it was heads out of the total of 50 times that we flipped it. So we're going to have 26 out of 50, which gives us a 0.52. So that means that the experimental probability of heads is 52%. So that means that when we did this experiment, 52% of the time we ended up flipping a heads. So let's do this one of what is the probability of buying a math book. So we have sales of books in different subjects from a bookstore. So we want to know what's the probability of buying a math book, since of course we're in a math class. So we have that the total number of books, we'll need to add that all up to see how many total number of books there are. So if we go ahead and add that, we get 44 plus 36 gives us 80, plus 24 is 104, plus 25 gives us 129. And we want to know the probability of math books. So if we look there at math, there was 44 math books sold. So we get 44 out of the total 129 books that were sold if we do that division. And then remember, we need to change it to a percent. So that means that the experimental probability of buying a math book is 34.11%. So that's quite a few math books that were sold there. So you get a 34.11% of people that were walking into this bookstore were buying a math book. So experimental probability practice. So we have the results of a spinner experiment. So if we had a spinner and it was split up to have X, Y, and Z in 3 different portions of our spinner and we spun it, we have the number of times that it landed on each letter. So see if you can figure out the probability of landing on the letter Z. Go ahead and pause the video. Alright, so now that you have paused the video, let's take a look and see if you got it right. So remember, we're going to take the number of times the event occurred. So z occurred 13 times divided by the total number. So 13 out of 20 gives us a 0.65. So that means that the experimental probability of landing on z is 65%. So that means 65% of the time that we spun that spinner, we landed on a z. So now let's talk about complementary events. So complementary events, whenever we have complementary events, it means that the event and the complementary event is going to equal 1 because they are complements of each other. So anytime you're dealing with complementary events, your probabilities are going to equal 1. So if we know that the probability of A is 0.27 and we want to know what the probability of the complement of A is. So we're going to use the formula, so we're going to plug in 0.27. So now to solve for my probability of the complement of A, I'm going to subtract 0.27 from both sides. So I get that the probability of the complement of A is 0.73, which I could change into a percentage and say that it's 73%. Alright, so let's do another example. So we got that this time the probability of A is 0.64. So I'm going to go ahead and plug in my 0.64 into my formula, subtract 0.64 from both sides, and I get that the probability of the complement of A is 0.36. Alright, so if probability of A is 0.91, what's the probability of the complement? So this is going to be one of your questions on your check for understanding. So this is the end of our asynchronous session 4. If you have any questions on any of this, please feel free to reach out to me so I can help you out with them.